I seem to be having some sound issues. I hope it's not too bad. You buy these things from Amazon, they seem to work for some time and then suddenly they die on you. But anyway, we need this concept of reverse weathering and alkalinity consumption or pH regulation in the long time scales to see how atmospheric pH is related to weathering and reverse weathering. This is the reverse weathering equation where you are again taking divalent cations combining with the weathered product of the silicate rock, and this is the carbonate alkalinity which is being used up in this reverse weathering reaction to produce what is called clay orthogenesis or in situ recrystallization, but the main thing we are worried about is that it releases carbon dioxide. Obviously this is already in the system, so it's not new, but to remove it you will need the weathering reaction again to go back from the silicate to this chert. So that obviously delays the carbon removal process overall. Alkalinity is a very hairy concept. It's complicated, lots of details which I'm not sure even I can totally explain without help. Alkalinity is defined as the excess of proton acceptor bases in a solution. Okay, alkalinity is considered a measure of a solution's ability to resist pH changes. We will see that the ocean pH has been well regulated for many million years, and we are changing that by increasing CO2 at a very rapid rate. Waters with high alkalinity have a high capacity to buffer against changes in proton concentrations, i.e. to reduce changes in pH. So the pH change will be controlled by the buffering ability. So here is something from the ocean science team, schematic of the carbonate system, ions and molecules in seawater, and some of the equilibrium reactions that occur among them. Sea surface conditions depicted at 30 degrees centigrade and salinity of 35. Typically salinity dependence is pretty large for alkalinity. So atmospheric CO2 dissolves into the water easily. Carbonic acid is formed, which is split quickly into bicarbonate and H+, which can then go into carbonate and H+. So these are the usual reactions we look at, but there are a bunch of other ions which together give us the total alkalinity of the ocean. So boron, sulfur, phosphorus, silica, they all matter for the overall total alkalinity. And the reverse weathering basically regulates atmospheric PCO2 through the establishment of a stabilizing feedback with marine pH. So there is a pH thermostat which works fairly well. This feedback operates in conjunction with the silicate weathering feedback that we've been looking at. Dependence of chemical weathering and erosion on temperature and rainfall, as we know. This will stabilize climate on longer time scales, which is what we are trying to learn. A more potent reverse weathering buffer, which is expected under high silica Precambrian conditions, greatly strengthens the pH buffering capacity of the ocean. So that's from this paper, but basically it's telling you that the buffering ability of the system itself has varied over time with climate change and tectonics and other things, and of course that also means that the atmospheric CO2 has been very different, pH has been different, alkalinity has been different. We already looked at this in other forms. So CO2 affects temperature and rainfall and runoff, which affects silicate weathering, which also is directly affected by temperature because warmer temperatures favor faster weathering rates. Silicate weathering of course affects atmospheric CO2, which affects ocean pH, and there is also volcanic degassing which affects CO2 of course. And this pH is what we are looking at here in this particular podcast with the reverse weathering and pH thermostat. And reverse weathering also affects CO2 sequestration rates. and silicate weathering affects carbonate and chert, which is basically silica. So to look at enhanced buffering ability, if we had only carbonate buffering, then CO2 going to H2CO3 bicarbonate, carbonate, and forming calcium carbonate is typically what we worry about, and how much of it gets rained out and sequestered and metamorphosis, etc., or becomes limestone depending on the processes. But when you have a clay buffer, which is what we looked at just now, we have in addition to the bicarbonate, carbonate, calcium carbonate, this divalent cations combining with silica to form the silicate clay buffer that we talked about. So these are important. So in the modern climate, basically when we come back to what we have already seen, it's the carbonate ion that gets consumed if the CO2 is dissolving at a faster rate than the equilibration time or the rates of these reactions. And consuming CO3 means calcium divalent cation, which is abundant in the ocean, is not going to be able to have enough carbonate ions to form calcium carbonate, which is what basic acidification is, because that reduces the supersaturation of calcium carbonate in the water, which would affect the calcium carbonate forming phytoplankton like foraminifera. So they cannot maintain their shells and begin to dissolve, like corals as well. So that's basic acidification for us. But this is the equilibration of alkalinity and pH. So we have pH here, alkaline things like fresh egg white, laundry detergent, etc., and acidic things like milk, black tea, vinegar, lemon juice, etc. And you can see the concentration of H plus here, and as let's say we focus on CO2 increase, which is what we are doing, the fractional contribution to consumption of H plus and change in pH plus happens by basically perturbations to carbonate and bicarbonate, and you can see this is much flatter here over a longer range of pH compared to carbonate, but carbonate is much flatter way out here, and CO2 is much flatter way out here. So the CO2 here keeps changing pH. Ocean has maintained its pH in this range for millions of years, which is shown here. So if we look at the Vostok ice core, we have seen before that the CO2 varied between basically about 200 or 180 to 280 to 300 or so, and we talked about the various hypotheses that exist for explaining this glacial deglacial CO2 change. Estimates of glacial pH and average interglacial pH remain tightly bound over this range here of 8.15 to 8.25 or so, but with global warming and anthropogenic activities, we are obviously increasing CO2 here very rapidly on the scale, and that means pH is crashing. Many places have already seen reductions in pH and acidification, but it can keep going unless we can control CO2 of the atmosphere. So we'll come back to this, including discussions we have had before about enhanced ocean alkalinity for regulating atmospheric PCO2 or drawing down carbon from the atmosphere. But in this context, I hope you get a sense of how reverse weathering is a part of the pH and PCO2 regulation. So basically it slows down the CO2 sequestration by consuming ocean carbonate alkalinity and decreasing pH. Okay, so that's why reverse weathering is a very important reaction, and on long time scales we are focusing here on carbon evolution and climate regulation. Reverse weathering is a part of the set of reactions we have to worry about as to how CO2 amount in the atmosphere and climate regulations have changed over time. So we'll look at the other details as we go forward.